Welcome to Team 3 Mini-Drone presentation for California State University of Los Angeles Unit Design. Hi, I am Lazaro Cano, and I'm accompanied by my fellow teammates Brian Santiago, Nikolina, Glamuzina, and Peiwei. We would like to thank our advisor David Scholler, who has been a great aid in this project.
In our presentation, we will cover the background, project statements of the Parrot Mini-Drone, the requirements of our mini-drone competition, a project overview of our project, software development for our Simulink code, and our mechanism design for our drone competition of this year's senior project, and the conclusion.
Here's a little bit about the background of the project. First, by explaining what UAV is. A UAV is an unmanned aerial vehicle operated without any human interventions. They're used worldwide to perform missions autonomously, such as aerial photography, delivery, combat, surveillance, and more. Our project will be using a Parrot Mumblefly with 4 sensors: ultrasound, pressure, IMU, and camera.
The object of this project can be explained in 2 points. The first desire was to modify a commercial drone to autonomously identify and fly a path, which includes developing a simulation code on Simulink and implementing that software onto a hardware of a Parrot Mini-Drone. The second was to develop a pickup payload mechanism attachment, wherein the drone will fly a path, retrieve a said payload, and return to its starting position.
We'll now discuss the requirements needed for the drone and for the mechanism. For the functional drone requirements, once the execute button has been pressed, the drone must start autonomously from a starting point. The drone will lift off to a designated altitude and will orientate itself, meaning it will stabilize and orientate yaw to follow a course. The drone will also identify a path and track the path to identify any course changes. If so, then the drone will move forward, left, or right with respect to the path. If any environmental disturbances, then the drone will stabilize and correct itself. When the path comes to a destination, the drone will land on the pad and shut off. Since the drone will have to pick up a payload, there are some requirements. Those being the drone must pick up an Rubik's Cube that's 3 by 3 by 3 centimeters and weighs 25 grams with the least amount of time. Not interfere with the drone's flight capability and sensors. Maintain a weight distribution, meaning the center of mass shall not change with additional payload, and the drone must remain stable as flying with the payload.
Within the project, the Simulink modeling took priority, with 2 major focuses: creating the drone to be autonomous with the use of state flow, and using optical flow alongside the camera sensor. Once the code was done, it was time for testing the drone hardware. For the pickup payload mechanism, it was designed, modeled on SolidWorks, manufactured, and tested. The competitions at the end of the school year are to show how the team fared with the project, testing how well their simulation ran, as well as how well the drone kept on the path on an actual run, and finally how well it can pick up the payload.
This is our work breakdown structure for the project. It's been broken down into 4 phases. Phase 1 was the Simulink simulation modeling. Phase 2 was embedding the software into hardware. Phase 3 was developing a mechanism. Phase 4 was participating on the competition, the expo, the final report, and the graduation. As you can see, the dark shaded boxes represent the completion of tasks for each of the phases. The light shaded boxes represented the upcoming tasks, which will be the final report, the competition, and graduation. Overall, we had 8 milestones throughout the school year. This semester, we had 4 major milestones. We done well on following the path on simulation and real time. We were able to successfully finish the practice simulation competition. The mechanism was fabricated and attached, and we are ready for the competition.
Let's talk about the software development. The coding was done in MATLAB using Simulink, optical flow, and state flow. The code has been broken down so one can understand what was done to make the drone autonomous. The image shown shows the flight control system. As shown, there are three major inputs to our control system. First input being the AC command, which is the initial control command that only tells the drone to hover, as well as the updated references commands. The second input is the drone sensors, which are the MIU pressure and ultrasonic, which helps identify the drone's altitude and identify any wind disturbances. The third input is the vision data, which uses the camera sensor to identify a path. These inputs are fed into the control system to generate the autonomous drone path identification, ADPI. As shown, there are two outputs, actuators and flag. After the code is generated, it sends the code commands to the motors to get the drone to fly. The flag is there as a safety factor. If the drone loses control and hits something, then it will shut off. Before getting more in depth into the control system block, it is important to talk about the image processing system block.
This is an overview of the image processing subsystem within the flight control system and is key in aiding the drone to following its flight path. There are three basic functions to this subsystem: identifying the color of the path of the drone and path edge discrimination, highlighted in the red box, and to use optical flow to determine the x and y velocities of the movement between consecutive images, highlighted in the blue box. Within the red section, two video viewers are used, one to show the video feed of the camera sensor and the other focusing on the outputs of the edge detection block. The inputs into this subsystem is the image data from the camera sensor, and the outputs are the vision data of intensity values and the horizontal and vertical velocity vectors. The main function of this subsystem is to identify the color of the path of the drone, this slide focusing on outlining the image processing steps. The input is the camera data that passes through a conversion block, returning RGB data, which is then checked for the dominant color, simply chosen to be red for this instance. Logic blocks are then used to binarize the image, meaning if the values returned are a value greater than the threshold, it returns a 1. If not, then it returns a 0. The binarized data is then summarized and passed through another threshold, which is then outputted to the control system. Extra blocks are used to aid in edge discrimination on the path, comparing intensity values at the edge detected to later aid the drone from overshooting the edges. Both visual data outputs are used for the drone to detect and follow the path in the control system. The third function to this subsystem is to use optical flow to determine the vertical and horizontal velocity vectors, located in the blue box. The inputs into this section of the code are the camera images and position values from a corner detection block. The outputs the velocity components. Optical flow is the distribution of apparent motion of brightness patterns within an image, the motion of the image pixels compared to neighboring pixels. And the Lucas-Canaday method solves for these apparent velocities by using least squares method. The MATLAB function block in the orange is a script that incorporates the Lucas-Canaday method. Errors using optical flow with this method occurs with low contrast and poor resolution of the images and large motions captured between consecutive frames. With the increase in error proportional to the frame rate, the time between consecutive images must be small to get feasible velocities. The corner detection values also help the drone focus on edges of the path during turns.
Here is the control system overview. This is where a code is generated to make the drone autonomous. Now this may look a bit confusing because there's a lot going on, so it is broken down into 4 sections to get a better understanding on what's happening. In section 1, which is labeled as black and white intensities, we will talk about how the output from the image processing system is used as an input to the MATLAB function and what the values display mean. In section 2, known as the MIU Dynamic Data, we'll talk about how some of the inputs from the MIU data, which is generated from the MIU sensors, are used as inputs to our subsystem to generate an output of yaw. In section 3, being state flow, we will talk about how the use of state flow was used to make the drone maneuver autonomous and the inputs needed. In section 4, being the updated reference commands, we will talk about how the outputs from the state flow and some inputs from the MIU are fed into the drone's motors. Section 1, black and white intensities, the output vision-based data from the image processing system is used as an input, which is the intensity value for red. That information is fed to this MATLAB function, which displays the intensity values of the surface the drone is hovering from. It displays the x and y axis intensities values from a 3D axis. Since the path is red and red has an intensity of 1, it will help map out the path as the drone is moving. How? While the drone will move towards or rotate to the axis that has an intensity of 1. It will also let us know the drone is within the path. This information is then fed to the state flow block for additional commands. In section 2, IMU Dynamic Data, the outputs are provided from the MIU data, which are yaw and initial body rates. They are used as input to a subsystem to provide the correct yaw needed. This yaw will allow the drone to rotate at any angle. The initial body rates go into the MATLAB functions to integrate positions to evaluate the R value respect to the drone's up position, and then subtract it from the yaw to give an output of the correct yaw, which is then fed to the state flow block.
Now let's talk about the state flow section. We named our state flow block ADPI, which stands for Autonomous Drone Path Identification. Before getting into the code within the block, it is important to understand the input that will be needed. As shown, there are 4 outputs. The first 2 being the position x and y axis, and the velocity respect to dx dy, which comes from the IMU data input. Next input being yaw value, which will be used to tell the drone to rotate, and the vision-based data intensity, which maps out the path. The output of the state flow will be yaw out, x out, y out, and z out. 3 output will be discussed in the section 4 updated reference command. Section 3 shows an overview of our state flow block that shows all the necessary command block that is needed for the drone to complete the path in Simulink. When running the code, the drone starts by reading its first command block, followed by an arrow pointing to the next block, and stops until completing its last. Each block provides outputs that is fed into the motor. These outputs are constantly being updated. As y'all can see, these command blocks were divided into 3 separate subsections to give the viewer a better understanding of our code. The first block would tell the drone to hover and move forward. Second block tells it to turn whenever the next red path is. And the third block tells the drone to land once the circle path is detected. In the next 3 slides, I will talk more about what each block does and the purpose for each subsection. Section 3.1 highlights our first subsection block in state flow, where the drone is asked to hover, move forward, and stop when each of their conditions are met. When running the code, the first block only commands the drone to hover at 0.914 meters off the ground, which is equivalent to 3 feet, for 4 seconds before moving on to the next task. This is to give the drone enough time to orientate itself. Anything less than 4 seconds will set the drone off the red path. The second block commands the drone to move forward when a red path is detected. As a quick reminder of our drone competition, the drone will have to overcome some wind disturbances somewhere along the drone's path. This wind disturbance will be represented by a fan. When a wind is detected, a counteract motion code will activate to help the drone move forward for when powerful wind is present. The way this code works is that it uses dx dy outputs from the IMU sensor to determine if the drone speed passes the 0.7 meters per tenth of a second rate. If so, then the input data x dy is subtracted by the same input dx dy as an input data constantly updates. Once the end of the red path is detected, the drone comes to a stop and follows the next command block. Here's a video that shows the wind countermeasure code in action. Notice how the drone comes back to the path after the wind blows it away.
Ready? Go.
Section 3.2 highlights our second subsection block in state flow, where the drone is asked to turn left, right, or 45-degree turn whenever their conditions are met. As mentioned on the previous slides, the drone will come to a stop once the red path is no longer detected forward. From the image processing block, an edge detection within the vision-based data input gives a matrix value of ones and zeros. The ones represents the intensity value of red, and it is used to determine the angle value in our state flow. This angle value will tell the drone to turn whenever the next ones are, before moving on to the next command block. Depending on where the drone finds its new red path, the drone will either make a plus or minus 90-degree turn or a 45-degree turn, and then moves on forward until the end of the path is reached. The next block tells the drone to stop and maintain its hovering position at 3 feet. Section 3.3 highlights our third subsection block in state flow, where the drone is asked to stop, land, and finish when each of their conditions are met. The first block commands the drone to come to a stopping point once the end of the path is detected. This is then followed by a landing code to help land the drone on a red circle pad at 0.1 meters per tenth of a second. Once the drone reaches below 0.1 meters in height, the final block commands the drone to reach 0 meters in the z-axis. As the drone hits the floor, a flag code that is found within the support package will activate and will then stop the drone's motor from spinning.
This slide will talk about section 4 of the code, the reference commands. When the drone turns on, it has a set of reference commands. Its position is its origin, and it doesn't experience any yaw, not moving until those reference commands are changed. The outputs of the stateflow block are combined into one signal, the updated commands, which replaces its original reference, which is then fed into the drone motors. With each new change in the state of the drone, the reference commands will be updated and the drone motors will react to those updates.
Here's the video of our Simulink code in action.
Let's talk about the mechanism concepts. Before designing the mechanism, we tested out that the drone can lift a maximum of 38 grams. The maximum mechanism weight will be 13 grams, and the payload will be 25 grams. The center of gravity of the drone is located at the camera sensor where the red arrow is pointing at. Starting off with the mechanism design. As for pros, it is easy to attach. It weighs 7.86 grams, and the center of mass remains at the center. For cons, it required 3D printing. It required replaceable 3M tape. It blocks the sensors after picking up the payload, and it is required waypoint follower when carrying the payload. The reason why we designed it like this is because the design will not block the ultrasound and camera sensors until the cube has been picked up. There will be no additional modification needed on the frame. There will be no codes required to control the mechanism. The mechanism will stick to the cube as the drone lands. Here is a video of the drone picking up the payload in action. The overall accomplishments for this semester were: the work breakdown structure was defined, the competition requirements were met, software development was completed, the mechanism model was manufactured and attached, and the drone is now ready to be deployed. This concluded our presentation. We would like to thank our advisors, David Scholler and Mike Thornburn, for being a great aid for this project. We would also like to thank the Cal State LA Engineering Department for providing this opportunity.